right, good. So welcome to Data Community DC. Data Community DC is an umbrella group that has several meetup groups. This one is Data Science DC. It's the largest of the meetup groups. So we also have Data Viz, DC General to the AI, Data Wranglers, Deep Learning Adventures, Statistical Seminars, our buddies, Power BI User Group, Statistical Programming DC, Data Education, and Full Stack Data Science. I'd like to welcome, I guess first let me ask you, how many people here are new, have not been to one?
Whoa.
Wow. Nice. Thank you for coming. So please take a look at our site, dc2.org. That's the umbrella for all of the meetups that we have. You can find the different meetups too also on meetup.com. We wouldn't be able to do all the things that we get to do without sponsors. And our organizational sponsor is Rotational Labs. Prima, are you here? Oh, there's Prima. Yeah, Prima from Rotational Labs.
Get my spiel now. So hi. My name is Prima. I'm one of the senior machine learning engineers at Rotational Labs. And so we are a custom boutique firm who specialize in building machine learning applications and data products for companies. So if you're kind of new to the AI space and want to get familiar with using like large language models and other machine learning tools to build products, we can help your team get up and running and help scale your business. And so there's my email. We also offer 30-minute brainstorming sessions to help you scope out your problem. And so you're welcome to either chat with me after today's presentation or email me at prima@rotational.io.
So one of the cool things about Rotational Labs is that they grew up in the data community. So the company actually were people in the community, and then they went to Georgetown, did some educational certificate in data science at Georgetown, and then created the company. And now they've come back to support our community. And I just think that that's really cool. Our event sponsor tonight is Neo4j, and they've got us 2 wonderful speakers, and they also gave us all the great pizza. So thank you, Neo4j. And we have an event space sponsor, which is Excella here, and they provided the space, which is really, really nice, and all of the drinks that we had. So thank you, Excella. So Data Science DC, the coordinators are, I'm Janet, and then we've got Jeff Hale, and then Abigail. I don't think she's here. But we're the 3 coordinators, so if you'd like to get in contact with us, please get in contact with us with our first name at dc2.org. We have a diversity statement and a code of conduct. Basically, we want everybody to be nice to each other, and if there's anything that doesn't feel right, please get in touch with me or Jeff, and we will make it right. Today's meetup is being recorded, and it'll be placed on the YouTube channel at Data Community DC, and then we also have a Slack channel, and we'd love to have you guys join us. Some upcoming events. So June 21st, we've got the weekly tech hangout online. It's by Women and Gender Expansive Coders DC. That is what Women Who Code is. That's the new local group for Women Who Code. June 27th, there's predictive latent class modeling, motivation applications and software. That one's online from 3 to 4, and that's being run by our buddies. June 27th is the monthly Data Viz DC. I don't know, I didn't see a topic on that one yet.
For the Data Viz meetup next week, we've got a couple of different talks, but the most interesting one is going to be making infographics in R Markdown.
June 20th and 21st, there's a free 2-day conference at Power BI DC. July 1, Data Wranglers has their noon to 1 online, and I think that's every 2 weeks that one is done. And then August 20th, Data Science DC, we're having a book panel on a panel of authors on writing a data book. And I think we also have another one coming up in July for Data Science DC, but we don't have that posted yet. So stay tuned or keep looking. Now's the time that anybody has any announcements for either other meetups that would be interesting to the community, anybody that's looking for a job or has a job that they like to fill, or anything that would be community pertinent. So, anyone have anything? Okay.
I do.
All right, cool.
Hi, my name is George Baden. I'm from a small company in Columbia, Maryland, called Impact Research. We're looking for a data scientist to help with some of our modeling activities, large language models. A lot of our work is for transportation safety. We work in the automotive industry. So if you know somebody who might be well suited, or if you're interested, please come find me afterwards.
Great, thank you. And a lot of times we do go across the street to Courthouse, so if you join us there, there'll be more people that will join too.
Thank you.
Anyone else? Will?
So, hey folks, my name is Will Angel. I'm one of the solutions architects here at Excella. We're an IT consultancy that help our clients solve problems with technology. We do lots of software development and AI analytics. We are hiring data scientists and MLOps engineers right now. So if that's something that you're interested in, helping our private sector or federal space clients in, come talk to me afterwards.
Hi guys, my name is Sunny, and I graduated with a master's degree in data science so long ago, and I'm looking for entry-level data scientist position. So in my academic background, I've applied data science and machine learning in a wide variety of physics research, and I would love to keep doing it. So if you know any entry-level positions, please do let me know. Thank you.
Hi, my name is Chase. I'm also looking for entry-level positions in data science as well. Recent graduate with also 15 years in retail analytics. Some of my company's clients have included large institutional investors in the past, but I also did CAD work for a long time as well, and just looking to transition into this space. I'm looking at government work. I'm looking at all sorts of opportunities out there. One of my focus in school was on NLP approaches as well. Sentiment analysis was focused on my thesis, and I'm also looking at other opportunities related to that as well. So if anyone knows anything, that would be very much appreciated to learn more. So thank you.
I'm George Zoro. I'm organizer of Deep Learning Adventures. I'm actually hiring at where I am right now at National Association of Realtors. So I heard some great candidates here. So I'm looking for a data scientist. This is for a real estate company that also uses tech. So if you're like home pricing and things like that, come and talk to me. I have an open role right now.
Anybody on this side of the house? Okay. Well, thank you. Thank you for attending. Thank you for being part of our community. Data community itself has 15,000 members, and it's nice to see such a nice large group coming out tonight. So with that, I'd like to turn it over to Cayley and Cynthia.
Hi everyone, I'm Cynthia Famano. I'm a sales engineer from Neo4j, and I'm going to be speaking to you tonight along with Cayley Hauser, who is a consulting engineer at Neo4j. And also in the audience we have Sid Beckett, who is also a senior sales engineer for Neo4j. So we're happy to, we'll probably all be going over to courthouse. If you guys have any questions for us, we'll be there. So today's presentation is about LLMs and knowledge graphs and how the combination of those two can prevent hallucination hiccups. So everybody here is probably familiar with LLMs. They're amazing. They give us opportunity to automate a lot of things, generate code, etc. But along with that, it comes with challenges. So LLMs are normally trained on a certain amount of data, and there's like a cutoff perhaps to the training data, so that new data coming in they're not always aware of. They provide reasonable answers to questions, but they may be out of context or not accurate. They can inherit bias depending on the data that they're trained on. Sometimes they lack knowledge of an enterprise domain, so depending on if they're trained on data that's on the internet, they may not have access to private company or corporate data. And they can never really attribute how they got their answer. So they can give you an answer, but they don't often attribute that to the source of the answer or explain how they got the answer. So because of this, we've seen a big push towards something called RAG, which is retrieval augmented generation. And this is becoming sort of an industry standard for GenAI and LLMs, where you have a sort of like a database of truth that helps verify the sources of the answers, provide domain-specific relevance, and then reduce the amount of hallucinations. So before Cayley gives her demo, I thought it would be good to just kind of go over some graph concepts. So we're going to be talking about property graphs. So a property graph is a graph that consists of nodes and relationships. The nodes represent persons, places, things, nouns, and these are entities. And then the relationships represent how the entities interact with each other. They're normally classified by verbs. Both nodes and relationships can have properties. Properties are key value pairs that describe the entity. And the relationships can also have properties, and the relationship properties sometimes describe the time period the relationship existed, or it could describe the probability, the certainty of the relationship, and other things like that. Relationships also have direction. So they can be like Andre drives the car, but the car does not drive Andre. So key differentiator of storing data as a graph instead of as a relational database is that the relationships kind of come right out at you, and they're explicit, they're stored as pointers in storage. So you don't have the thing about going into like relational matching foreign primary keys, doing table joins, etc. It's just natural, like the way it's designed is the way that you see the world, and it's easy to understand, and it's easy to traverse relationships. So graph databases are just kind of an evolution, even though graphs have been around for a very long time. Graph databases are relatively new. And the benefits of graph databases are that when you have data that's highly connected, it makes it very easy to query that, and very efficient when you're querying across multiple relationships. It's also very agile in that you can add new entities and relationships without having to refactor a schema. So our world is full of graphs. You might think of a subway system, a power grid, here we're showing, you could look at this and you could say, well, I can see the highways and the roads that connect various cities together. So graphs are everywhere. Some of the use cases for graph databases exist in financial services, looking at risk analysis or transaction fraud, manufacturing, looking at logistics and supply chain, consumer retail, where we're looking at like recommendations for customers, energy and utilities, doing digital twins of power grids, life sciences, doing research on new drugs or cancer research, and also there are many applications for graph in the federal space. So with the advent of generative AI and LLMs, knowledge graphs have kind of bumped up their importance in that as a data source for generative AI. And to distinguish a graph from a knowledge graph is just adding semantic or context into the graph. So this could be an ontology, a taxonomy, which is also stored in the graph, and the different entities are then connected to that taxonomy or ontology to provide the ability to do like semantic and contextual searches. Gartner identifies knowledge graphs as a key enabler for generative AI, and I think you'll see that when Cayley does her demo, how that's true. Graphs allow you to combine structured and unstructured knowledge. So you may have a lot of unstructured data, articles, etc., that are represented, and then you have entities that these articles contain. You know, the article could be talking about a person, a company, an address. So these entities, sometimes they are extracted from the articles and put into a graph. But then the articles themselves have textual information that can be represented in a vector format. So Neo4j as a property graph database can store these vectors as properties to the entities. So you may hear the term GraphRag. So GraphRag is retrieval augmented generation, where you're using a knowledge graph to supplement the LLM to provide more accurate and attributable answers to the question. So user asks a question, the question is then translated into a vector. The LLM does a smart search comparing vector similarity, and then it can convert also to a query to the graph database, which then returns more relevant info. Other people, places, things that may be relevant to the question, and then combines all that relevant info into an enriched answer and an attributable answer. So that was my quick overview, and I now want to hand it over to Cayley, who's going to give you a really cool demo of how all this works.
Thank you for that great introduction, Cynthia. And I'm going to put that QR code back up at the end of this. So, because I'm going to be mainly going through some code very quickly, some examples, and you'll be seeing data and things flying here and there. So, first thing I'm going to have to ask is that if you could save questions until the end, that would be really helpful because you don't want to get me on a tangent. If you want to get me on a tangent, you can catch me at Courthouse afterwards. But I have limited time and I want to make sure that I get us through all of the material. So real quick, my name is Cayley Hauser. I just got married, so I almost threw on the last name. Cayley Hauser, thank you. I've been working in the data science space for a few years now, since around 2017. Most of my experience is in the federal space, in the defense space, but I've also gotten to work on projects in the nonprofit, banking, and real estate industries. So I've been really grateful that I have been able to see data science across a broad range of topics and applications, and I've done everything from visualization to machine learning with supervised, unsupervised learning, but graphs is one of the things I've become really passionate about. And the reason for this is all of you know as data scientists or aspiring data scientists that we're always talking about data, right? If you really remember back in the day, we used to talk about the 5 V's of data. It's kind of become ubiquitous, like all data is pretty high volume, high veracity, right? So when I was talking about LLMs, knowledge graphs, I mean, your grandma might not know what ChatGPT is, but your parents probably do. And so it's becoming more and more standard that we're talking about data all the time. And that's why I'm so passionate about graphs, because graphs naturally enhance your data. And we'll talk about that a little bit more, but that's gonna be the core of what I focus on. We're gonna talk about data science, we're gonna see algorithms, we're gonna see visualizations, we're gonna see LLMs. But remember that all of it is powered by the inherent structure, connectivity, and context that we get from graphs. And that's why I loved it as a practitioner, and that's how I came to work for a graph database company myself. So, but you're all here for LLMs, right? I'm very excited to be here presenting because I am a consulting engineer. So most of the time I'm head down with the customer all day trying to productionize their system, full stack, graph, everything from graph data models to data science. We're doing everything, right? And I'm excited to see LLMs become more popular and they're actually getting productionized. But we talked a little bit in Cynthia's presentation about some of the drawbacks of LLMs, right? Hallucinations, inaccuracies, lack of context. I think a great example is, has anyone here heard about the lawsuit in Canada regarding the LLM with Air Canada? Yeah. So if anyone hasn't heard about it, Air Canada, great idea. They said, oh, we'll make a little chatbot that just pulls data. So they said, here, chatbot, here's our policies. Go talk to customers. Make this so much easier. We won't have to hire as many support people. This is great. So customer was asking about a specific policy related to a refund, and the chatbot said, yep, you're good. Here's the refund, here's the policy number, because you know, LLMs, they can be wrong but strong. They're very confident. And so this guy, he's like, you know, very smart. He said, I'm going to take a screenshot of this. A few days later, he comes and he calls and he says, hey, I want a refund. And they said, can't have a refund, sorry. And it turned out that the LLM had just made things up completely. It was not accurate at all. And so clearly they weren't doing RAG quite in the best way. And instead of giving him his refund, Air Canada decided they would go to court and say, we can't be responsible for what our LLM says. It's out of our hands. And the judge said, no, that's not how we're going to do this. And so it's becoming a real concern, right? You don't want to be legally liable if an LLM just starts making stuff up. And like we said, we can't always trace it. If we're just asking an LLM, you don't know where it came from, you don't know the context. And so that's why we want to be building in retrieval augmented generation, using it on our own data. And especially because you don't want to train an LLM on your data. That's expensive, it takes time, then you have to gather all your data into one place. The benefits of GraphRag is you can use what you have already in the structure of your graph to help ground what your LLM says. So, all right, that's enough intro. I'm going to go ahead and get into our demo now. So this is the cute little message generator, like a little happy emoji. And this is just for the purposes of a demo, and you can see I've kind of already run this once, so we can run it again. It takes about 10 seconds. So I'm always afraid to like ever press run on a demo, you know? I'm like, I don't know if I prayed enough to the demo gods today. But what you can see is this is generating an LLM prompt here. And so I've put a customer ID in here. In real life, of course, if we had an app, this would be pulling all that information, right? But I put in a customer ID based on something in our database, and you can put in a time of year, I put in my name, and an interest. And what this LLM is doing is it's generating some really happy, flowery text, flowery because it's summer. So it's saying it's a summer season. Here's your summer things, because it understands the time of year, right? You're giving it some things to say. But it's pulling up a bunch of articles of clothing, because this is a customer shopping data set. It's the H&M data set. If any of you have done some Kaggle things, it's in a lot of those. And this has real customer purchase data, and we'll look at the data in a second. But as you can see, it's first pulling up some items that are related to my search term. But what you don't know is not only is this pulling up some things that are semantically related, but it's also pulling up results that are based on the customer history of this customer ID. Now you wouldn't know that because obviously this isn't your purchase history or my purchase history, but for this customer, this is actually based on the things that they have purchased, and we'll talk about that in a little bit. And then it also says, you might be looking for some addresses, but here's some other ideas that are also still related to customer history that you might be interested to purchase. And that is all happening because of our knowledge graph and our LLM. It's giving us semantically related things here, similar in my search term, but it's also giving us personalized information, which is incorporating context and past behavior. So today we're going to talk about how we got to this point and what makes GraphRag pretty cool. So I'm going to go ahead and go to my graph real quick. I'm going to refresh it one time. So I'm going to be showing you little visualizations. All right, let's render today. But as you can see, I've got a little schema here. I'm not wanting to show it in the way that I want it to look. There we go. So I'm going to show you what our graph looks like. And so we have 4 different types of nodes in this graph. It's very simple, but for the purpose of a demo, we don't want it to get too complicated, right? We have customers here in blue, so this is a subset of our graph, right, of customers, and they have some properties. A lot of the customer stuff's redacted, right? So it's real data. And customers purchase an article of clothing, right? So this is going to be a specific, maybe a red, some kind of, sweater. And then each of those articles comes from an overarching product. Usually most of the articles are different colors, right? So you purchase an article of clothing, it comes from a product. And then each of those products, I'm going to each of the articles also has a department. So this H&M, they have like a bunch of departments. It's more than just shoes. It's like the tops fancy jersey. So they have very fine grained information here about the articles of clothing. And you can see we also have our customer purchase history, which we'll talk a little bit about. We'll talk about it now. So what you can see here is that we have very good structured data in this information, right? So you can see customer purchase history. So this customer purchased an article of clothing twice. You can see when two customers might be purchasing the same article of clothing, right? So they have some interest in common. You can see this person bought the same article 4 times. They must really like that piece of clothing. If you look closely, you might see some people doing my favorite thing, which is to buy the same thing in different colors. It's a strong habit of mine. So you can see all this customer purchase history, and it also gives you the history of the article as well, right? You can see how many people have been purchasing it. And I'm not going to get too deep into the data for purposes of this demo and for time, but if you were going to dig into it, you could see a lot more information. You could see, right, when things were purchased. You could filter that out. There's a lot of data exploration pieces that you can do with the information that's in this graph because of all these properties and all these connections. And you can immediately see that storing this data in a graph allows you to literally visualize those connections when it's in a visual representation. And this is what I was talking about, what Cynthia mentioned at the beginning of the presentation, is that graphs inherently show you those connections and those contexts. That would be a lot more difficult to see if you had it in a tabular format. You could join things and look at items like that, but being able to see these connections and follow these paths, you're going to see is really useful as we move on. That's the structured portion of our data. We also have an unstructured portion. So I'm going to go ahead and just look at some of the products for now. You can see that these products have a lot of textual information. This is that unstructured, that thing that we were talking about. And like Cynthia said, you could do some entity recognition models on this, right? You could make, a certain thing into a node itself. But what we're going to do in this case is we're going to use text embeddings to capture the textual information saved here. So you can see we have a bunch of textual information. We'll go ahead and just look at this one. So you guys can read that. So you can see we've got some detailed information about this product. It's called a Peter sweater. It's an oversized top. It's sturdy sweatshirt fabric with drop shoulders and ribbing around the neckline, right? So they've got a lot of information about that. And you could make some sort of database with a bunch of columns and one hot encode and try to use that for similarity, but that's going to get really messy and it's going to be a lot of manual labeling of work. You could train a model on it, but even then, we can do this really easily with text embeddings. So what we did with this is we took the information for product, so they each have some sort of paragraph of text. We embedded it. You can use any text embedding model. We use OpenAI, so like 5 cents later, I had a bunch of embeddings. And then we save those onto the product nodes here. So now I have a big vector, that really long vector, I'm not going to make you look at all that, that represents the information in this text. And again, this is all standard. You don't need graphs to do this, but I'm going to show you how we can use them. So if you have a embedding vector here representing text, I can look for similar vectors, right? I can do a vector search if I store those to find semantically similar products, right? So if the vectors are similar, then I should be getting something that is similar. So I made a little scene action. This just calls some code in there, and that's going to give me the most similar sweaters to this sweater in particular. So you can see if you read these, they have a lot of similar words, right? Ribbing around the neckline, cuffs and hem. We heard that drop shoulders, and it's very effective at finding those similar products. And this is capturing that semantic information. But it's only capturing that semantic information, right? We just did text, and now I'm getting similar products, but that's not capturing all of that customer history that's right there in that database ready for us to use. And using that customer history, using the structure of your graph, using connections, and combining structured and unstructured data is what takes it from this, which is good, right? Okay, here's one product, find me things that are similar, that sound similar based on the description. That's good. To better, here's some recommendations based on what you might like, or maybe what people who have similar tastes to you might like, to great, which is when you can eventually feed that information into an LLM and wrap it in nice, beautiful, punny words and make the customer very happy. And this is what drives customer engagement and satisfaction. And when I say customer, I know we're specifically talking about clothing data here, right? But this goes for any industry. Even if you're not doing a recommendation for customer purchases, which is what we typically think about it, everyone wants to get answers to their question efficiently. They want them to be correct. They want them to be based on their personalized data or their specific data if we have it. And that is what makes this useful across industries. All right, gotta keep myself on track. Okay, so we can get customer history by the structure of the graph like we talked about, right? So if I had a specific customer, I can trace their information like we saw before. Oh, no, there we go. So you can give it a specific path query and tell it starting with my customer, find me the articles they purchased, right? You can see how we end up really querying a path and which is really great for graphs and which I think is a really easy way to query things. So you can see that when we get this information, we start to also see the interactions of people with similar tastes, which is what I mentioned before. And what we're going to be able to do is enrich our graph with a relationship called customers also like. And we'll talk about where that comes from today. But that's a lot of information. I'll show you how we got there. And this is a really rich data, as I've been talking about for the last 10 minutes. And this is just one data set with 4 types of nodes. The other great thing about graph databases is how easy it is to add more data sets into here, right? I don't have to reformat my data if I have reviews, perhaps. I could add that as a node, or I could add that as a property. It's really easy for me to integrate multiple data sets. So again, for today's purposes, it's pretty simple, but it can get a lot more complex as you go. All right, so let's scroll through the notebook really quick, because there's a lot of things I want to talk about. So like we already talked about, we took the detailed descriptions for every product, right? Remember we had that string and talking about that sweater or whatever. We embedded it with OpenAI, and we did a vector search. Just like you've done before, just doing some cosine similarity. And again, at the end, I will have a QR code for these notebooks so you can play with them yourself. Because I'm going to be like scrolling through this like crazy. You don't need to start with a specific product, right? So if you take a search query, like a string, if you're looking for oversized sweater, you can embed that, right? So you don't have to start with an existing node. You can say, show me oversized sweater. It's going to make some new big vector. And then you can do the same thing for running some Cypher code that's just our query language, kind of like SQL. And you run that, it gives you the same thing as we just saw, recommendations based on that input vector. And like we talked about, it's going to look like a bunch of nodes. But we have another way to do this. The preferred way is with LangChain. So if you're familiar with LangChain, very great LLM-based company. They do a lot of cool stuff. They have an existing way to do this, actually with graphs and with Neo4j. So without having to do those steps sequentially, like, okay, let me take that search term, let me embed it, let me go put it into the vector search, and then let me return those. They have a built-in class to do it. So you just have to feed it the information, you tell it which embeddings you want to use, and it does all of that in one. So you just give it the search term, it embeds it, it runs it on the index, finds similar nodes, and returns to you. Okay, we've all seen this trick a bunch of times. And if we had a longer demo, I would show you some different ones. My favorite one is I put tennis shoes in and it knew that sneakers were the same. And trainers, which I thought was, I just think embedding models are fun, that it understands the semantic similarity. But let's start incorporating some of that structured customer history information. And I'm going to show you how we do that. This is mainly a lot of notes saying what I'm showing you on the screen. So let's add in that information. So looking at these customer histories, like we talked about, we're going to use the structure of the graph that we have here to add that customer history in. And I'm going to, without trying to explain to you the code too much, I'm going to explain what this is doing. So like I talked about, it's returning the semantically similar nodes when we do that vector search, right? We give it a query. It says, here's the top 10 products that sound the most similar, but looking at the text to what you want. But we're going to add on to that. So we're going to start with those. We're going to start with those similar products and those similarity scores. And we're going to run a path query looking for that customer history. So starting with the specific customer, I'm going to read this backwards just to make it easier, right? So we're going to give it some customer ID, right? That specific person. You're going to look for articles that they purchased and go back to, and then we're going to look over here to see if there's another customer who purchased the same article, who purchased, I know it's getting complicated, the product that we returned from the semantic search. So to explain that really complicated path query again in English, what we're looking for is, are there customers who bought that semantically similar product we found from the vector search, right? So we say, oh, this might be similar to what you're looking for, who also bought an article that the target customer bought. So if I have a similar taste as Cynthia, we both buy some of the same clothing, and then I do a search, and one of the products that is semantically similar based on that text is something that Cynthia bought, that's going to increase its score for me now. So now I'm doing some math to just add it into the score. Why? Because it's saying, yes, semantically similar is good, but if somebody who has a similar taste to me is buying something that's also semantically similar, maybe I should rate that higher, right? Because textual information can only incorporate so much. There's a whole sense of customer history and a sense of style that's not really captured in those text embeddings alone. And when you add these things together, this is giving you a semantic search, adding on customer behavior and customer history all in one. And so when I do that, and again, I'm sorry, I'm scrolling through this real quick, but I promise you can look at it at home. It's going to give you a different set of results with a different score, right? Because we added in this new score, boosting it based on if customers who like the same things as me are buying that semantically similar product. And what you can see in this little table, just doing some joins and merges and pandas, is that here's the new score, and this is the original score. So you can see that out of the new top 10, actually none of them were in this vector top 10 for this example, which means it's bringing me back a totally different set of results because it's now weighting it more towards my behavior as the customer, what I thought, and what people who are similar to me are interested in, as well as, of course, still incorporating that semantic similarity, right? Just because I might like pink tennis shoes, if I look for a black hoodie, it should still be looking for something similar to what I'm asking for, right? So this is, we're starting to build the blocks together, right? We had textual embeddings to represent that unstructured information. We use that to bring back related information to our search. And now we're saying, okay, but weight it more towards what my personal interest would be based on my behavior and the behavior of people who have similar tastes. And that's all great. But we're going to take it a step further because we're going to start using graph data science. I know graph. We're here, we're 45 minutes into the meetup, and we're finally doing the data science. So there's a graph data science library that we use, and again, I won't get too in depth into it, unfortunately, but I will give a quick overview and show you how we're going to use it. So we're going to make a graph projection at first. This is just looking for the specific subset of the graph that we want to run some algorithms on, putting it in memory. So what we're going to look for is we're going to look at this path. This is the path query again right here. So an article that's been purchased by a customer who purchased another article. So just looking for that part of the graph. And we're going to run an algorithm called FastRP, which is another embedding algorithm, and it's specifically for graphs. And what this is doing is for each article, it's embedding the neighborhood around that article. So what it's doing is it's translating the nodes and relationships around it into an embedding vector to say, this is what this part of the graph looks like. And so that ends up with a bunch of vectors that say these two nodes are more similar based on the structure of the graph. And I'll go back to the graph real quick and show you now before we had text embeddings on the products, but now we have fast RP embeddings on the articles. So this is capturing, because we used a projection based on customers, right? So we're just including customers and articles in this one. It's capturing the customer purchase behavior for that article. So it's generating these embeddings. And now that we have these embeddings, we can just run a graph k nearest neighbors on it. And it's gonna, similar as before, it's gonna give me the most similar articles, right? Because we just put these embeddings on the articles. And now, what can I do? I can write that information to the graph with that, as that customers also like relationship. So you see how we're enriching our graph with more and more information. And now I can write the results back to my graph, which just enriches it even more. So that's where we got those customers also like relationships. Those weren't in the graph before we ran this algorithm. So I'm going to dismiss other nodes. I'm going to show you, see that this one has 16 customer also like relationships. And again, if I expand this, again, don't get this to be too crazy. All right, you never know, some of them have like, customers buying a whole lot of them. But if you start to expand it, you'll see where these embeddings came from, right? It's because customers are co-purchasing these products. And so that's how the embeddings are made, and that's how the algorithm calculates this information. And so, sorry, I'm getting ahead of my own notes. All right, so you can see this information, this customers also like information is not, even though it's based on embeddings and there's an element of not full explainability, it's still pretty clear where this came from. This information was already in our graph. We had this information about who purchased what article. We see who's buying similar articles. We're just enriching this information. And like I said before, this customers also like relationship is really easy to understand. It's really easy to see. It's really easy to analyze. Like this, I love graph visualizations because if you're doing analysis, it's really nice to be able to see that information in front of you from firsthand experience. And now we have another layer that we can add to our search that we were talking about. There's some more screenshots. So now we're going to do something similar. And again, I know I'm explaining code, which isn't always fun. But what we're doing to make it easy is we're doing the same semantic search. Always start that semantic search because we want to make sure we're getting what people are asking for. But now we're using that customers also like relationship. So we're saying that semantically similar product. We want to find the articles where a customer also like, right? They have that relationship in the middle to give us other products. And then we're incorporating that information using the new relationships that we've added to our graph with our graph data science algorithms. Once we've done that, we're going to similarly increase that score if there are more customers also like relationships. And then we are returning the co-purchased product. So instead of returning the semantically similar product, we're using that to give us a place to start. We're increasing it based on if customers also like similar products to our target customer. And then we are returning those co-purchased products to the person who's inputting that search. Explaining a lot of code at once. But that is going to give us a different set of results that are based on our data, right? That any LLM is not going to have our data unless it's trained on it. That's based on the specific customer. That is based on their purchase history. That's based on the history of the article of clothing and who else is purchasing it. And that is based on that semantically similar vector search. So we're incorporating structured, unstructured, history, all of those things in one by using a graph. And to put it into an LLM, all we're doing is running that pipeline that you saw, that query pipeline, bringing in those results, and giving it to the LLM and saying, hey, you are really good at puns, you're really good at being nice to the customer, I'm going to give you the time of year, I can give you some more information, you can spice it up, and you're going to write this beautiful email to the customer that gives them exactly what they want or what they asked for, right? Because when I say what they want, I'm getting ahead of myself. we've been talking about searches this entire time, but these customer also like relationships are what allow us to do it without a search, right? So if I'm this customer and I purchase this, I now know that they might also like this sweater. And so it allows you to, in this case, give customers product recommendations even without searching anything. It gives you all this information in one, which I think is exciting. So let's talk a little bit about what we just did, because I know I went through so many steps. We started with a graph. I talked a lot about graphs and how I think they're cool. We talked about vector search or text embeddings to look at the unstructured information. We moved on to adding in some path queries, right? That's just looking for a path in the graph. I'm looking for customer and they purchased an article, and you can see kind of steps through the graph to add in customer history. And then we said, okay, if this is semantically similar and people who like the same things as my customer bought it, I'm gonna bump it up and make it a higher search result. Then we used graph data science to add the customers also like relationship by saying, okay, let's look at the customer purchase behavior for articles. We'll embed that with an algorithm, find the most similar articles, and we'll write a relationship to represent that, saying if these two have similar fast RP embeddings, then we say customers also like it because that means similar customers purchase it. And then we use that information to produce either really good search results or even just use that information to recommend to customers things that are relevant to them. And then again, we just toss those results to the LLM and say, don't make any stuff up, please. Only use these. Because you have to tell it that, or it will get excited and start coming up with its own products because they're very creative. So at the end of the day, we want to go one step further than just the tabular, just the graph. We want to use LLMs, but we want to ground it on our own data using RAG. And we can do that in a really explainable way with graphs. So you can see that I can tell you, as I talked about, exactly how we got here. You can look at the graph itself and understand why it came up with the answers that it did. You can see that it's easy to combine structured and unstructured data. Like I said, it's possible if you want to pull out the unstructured information and put it into a structured format as well, but it's also really easy to do with embeddings, as we saw today. And using vector search, cipher traversals, which is those graph traversals, on top of our enriched data with our keyword searches, all in combination, they yield optimal and personalized results. And then the other thing, of course, that we didn't do in this example, right, is you could have logged this information, you could make it into a chain, you could pass it back to the LLM, you could have customer feedback. There's all sorts of things you could do in real life when you're productionizing an app. Today, I'm just showing you a very quick demo. In real life, I would not productionize it in a Jupyter notebook. But this is where we're moving in the future. And you can see that graphs, because of the inherent structure of the data, why we talk about graphs so much, really lends itself to making these things simpler, faster, and more accurate. So overall, this just accelerates your app development. If you have your data in a graph, and like I said, this is a pretty simple graph. This would not be very difficult to put into a graph with 4 node types and some properties. It's easy to get your LLM prototypes, especially up and running, and it's easy to expand to additional data sets without loss of quality or losing result explainability. So that is my demo for today. Thank you for flying through that with me at a breakneck speed. And I will now open it up for questions.
What about using near synonyms to offer things that aren't the same thing to the user? Like if you're looking for poker games or books on poker,
Right.
I don't want to give them 5 different books on poker. I want to give them maybe 3, and then I want to give them books on other card games.
Yeah.
How would you manage that?
I would, so if that was my use case, I would limit the top results to 3, right? Of course, so I would say, okay, give me the exact semantically similar results, give me them exactly as I want them. And I would probably do an additional filter or change my graph pattern a bit for the second part. So I might say, give me card games. I might say where the product description includes card game, right? I might add some additional filters to my graph pattern so that I'm returning something more specific. And then I think the question here.
Yeah, this may be a basic question, something new to grasp.
No, it's okay.
But let's say you've spent a lot of tech debt to put your data into an SQL database,
Mhm.
right?
Yeah.
So what is like a best practice for if you wanted to translate some portion of that database or all of it even into like a graph?
That's really common. So it's going to end up being, it's very common. It's going to end up being dependent on, of course, the specific customer, the level of technical debt, right? I see this a lot. Some customers simply plug their graph database to, they feed some of that SQL database into their graph.
Can you just repeat it louder for?
Oh, I'm sorry.
Repeat the question.
Sorry. The question was, if you're an organization that has amassed a large amount of technical debt, putting this into maybe a tabular database, for example, like a SQL database, what's the best practice if they want to move some or all of their data to a graph? So I apologize. So the answer to the question is, I would say it depends, of course, right, on the customer needs. I have seen some customers are migrating fully to a graph database. A lot of them start with just feeding in a subset of their data, right? So they might do it for, maybe for testing or for visualization, right? Something like this. They might use it for graph data science. The in-depth conversation that we can have at Courthouse is it really is going to depend on how the dependencies and things like that. But it's pretty easy to feed data into a graph format. More of the decision is how do you want to format your graph, and that usually depends on the use cases specifically. So,
I'm just
yeah, sorry, same here. Yeah, go ahead.
Also, there are a lot of customers who actually keep both databases. You only bring in what you need to find those connections because those connections are stored in Neo4j to make those joins a lot faster. So I've been on projects before my Neo4j time where we actually hit Neo4j to find those connections, and then we hit a relational database to find the additional details needed to finalize a report, for example, and it was a lot faster than just hitting that relational database and relying on joins alone.
I definitely don't want too many joins. Question in the press?
Yeah, a lot of questions over there.
Oh, sorry. I'll start here.
Alright, so same kind of question, but if you have unstructured data, so let's say you have a novel,
Yep.
and you want to define all the relationships in there, who's married whom, like all that kind of stuff, but you don't want to do it manually. What would be the best way to do that?
So there are multiple types of models that do entity and relationship extraction from unstructured text. So I'm currently on a project where I'm working closely on this with a partner where they are training ML models on unstructured text, and it's pulling out those entities, pulling out those relationships, and then writing them to the graph. So there's multiple kinds that I'm not an expert in which ones, like they're kind of one of those things where they keep coming out with faster and better ones. So I'm not exactly sure what the most recent one is, but that is a common use case. Right, behind?
Yeah. Have you experimented using an LLM to generate those path cycle code?
So I have not personally done it as much, but some of my coworkers have experimented with using LLMs for cipher generation. They're not as good as SQL, which makes sense because SQL's kind of everywhere, right? But they are improving, and there are some that can create those cipher queries. But on the other hand, I think it is good to be aware of the structure of your graph and make those queries thoughtfully. So I don't know. I'm sort of like an AI, yes person, but sometimes I'm like, I don't know. I'm not always sure about it generating code yet, but it can. So you can certainly try it. All right, there's so many questions. Behind there.
So what are the general advantage of graph RAG versus regular RAG?
So a lot of it comes back down to what I was just talking about the advantages of graph, right? So all of your data is stored in your graph. It's connected literally, which is also how our brains think. When it, by design, captures those contexts and connections, right? So if I have this in a table, you think about that, it's going to be a lot more, like this is actually exactly what got me into graphs. I had a project where everything was in a table, and the analysts were literally trying to find connections between those rows, and props to them because I don't think I could have ever figured that out without a graph. But by having it represented in a graph that captures that context, it's very explainable, and it also allows us to generate that new information like those customers also like relationships and add it back to the graph, which just makes it richer. So it all kind of comes back to just graph as itself. All right, I know we're at 8 o'clock, So, okay, we'll keep going.
From the evaluation perspective, how do we know that the end results are better than the rank-based results, and how do we perform the evaluation from the customer perspective?
That's a
What
good
do you
point.
think?
I would say because in this case, I have that explainable chain to advocate for it, right? So I know for a fact that what's coming back to me was co-purchased, right? It is not only semantically similar, but I know for a fact, based on the way that I did this information, that people who have similar taste to my customer purchase the same thing. Now, of course, we are talking in the realm of fashion, right? So I can't ever really guarantee that someone's gonna like an article of clothing because, of course, there's a subjective thing where someone looks at something and they go, I don't like that print. You're like, it looks just like the other one. They're like, nah, I don't like that one. So to some extent, I can't promise for sure that a customer will always like the top result. But in something where this might be more of a hard and like fast answer, like maybe if someone's querying for a specific document, right, or specific instructions, it should be getting you information that is closer to what they want because we'd be incorporating both their input search as well as whatever similar information we have based on the structure of the graph.
Thank you.
Front row?
Yeah, so it looks like you've kind of optimized, what you're showing here is an optimization for like a similarity-oriented query,
Yeah.
right? So how do you tell the LLM not to respond to something that's not a similarity query?
Not a similarity query.
So, yeah, because it's like, it's you know, if you ask something that's not a similarity query, then it's gonna hit this
Yeah.
machinery here, or like what does
That's
that
a
mean?
good point. So what I would do is I would completely tailor the whole chain that you saw to what their what the specific input is, right? So in this case, as I was going through it very quickly, what I didn't really emphasize is I'm telling it like what index to hit, right? So I'm giving it a specific chain in the graph, and I'm saying look at customers who purchase articles, right, that are variants of products, and I'm telling it, you know, look at this index, look at this embedding. So what I would probably do if I was trying to build a all-purpose app, maybe, for example, as I was trying to say do similarity and do this, I would probably have different indexes, different chains, and I would tell the LLM that. I would, again, I'm not a prompt engineer, is what they're calling it these days, so I won't claim to be an expert in that, but you would have to tell it, like, sometimes a customer might be looking for similarity, and in that case, use these results. Sometimes they might be looking for, you know, something else. Sometimes they might be looking for how to return something, right? And in that case, go to this. And so you'd have to have a similar workflow to what I did, but with a different, you know, different results, and then you'd have to prompt the LLM to understand the difference. And I know that LLMs, it's a trial and error, right? Trying to tell it how to do what you want it to do, and it makes mistakes that you would never think that it would make, like making stuff up. And so you have to be very, very aggressive telling it what to do and what not to do. Blue shirt?
Yeah, so at the end of your demo, you end with the data frame with the top products.
Yeah.
How do you convert that to the actual LLM chatbot, and do you find that has like 100% success rate when you say like, here's what our top ones are, and I go tell the customer, like it could then inject whatever and talk about.
Yeah, so far, I haven't seen it do that. I have a coworker who does this demo more often than I. She said she's seen it do that once or twice. If I can find the code. Because, what's my prompt?
What was the question?
The question was, at the end of the demo we talked about, we got a data frame, right? A table. How do we give that to the LLM and tell it what to do? So what we're literally doing is there's another question.
No, it's going to give you the answer, but good.
It just is it's being passed into the prompt that we're giving to the LLM. So you can, do you want to add anything?
And sometimes you can even use different LLMs that are better for answering questions, taking the results and providing an answer, but a lot of it's controlled by like a prompt template to kind of explain how you want the answer to be provided.
Yep, so you can see here, you're just passing it the list, and it says, please only mention the products, don't come up with anything new, as creative as you are, please include the URL, right? You have to really, like I said, be very thorough with your LLM sometimes. But they tend to give pretty good results. But of course, again, it depends on, like Sid's saying, the LLM, it depends on what you're trying to make it do, and there's LLMs that are specifically for different things. So as you're experimenting, of course, it's probably worth trying the different LLMs. All right.
Can we get the QR code, please?
Yes, my bad. I apologize. I was like so into the questions. Thank you for reminding me. Oh, there you go. So that should get you to a Google Doc where you can see there's 3 different notebooks. There's one that generates the data, and you can also download a data dump, but there's one that generates it. So if you want to like go through the process of doing those OpenAI text embeddings, it costs like 5 pennies. So, or you can just load it from a dump. You can play with all this in Neo4j, which you can get for free. You can either download the software on your computer for free on desktop, or you can go onto Aura, which is our cloud-based software, and you can play with it in the cloud, also on a free instance. So you can do all that with those notebooks, and you can try yourself. All right, back corner.
Can you tell me some technical details about how you embed a part of the graph? Is it like a node plus one layer, or is it something more customizable than that?
Yeah, it's based on the specific projection that you feed it. So what it was in this case was you had a customer purchasing articles. So if you, there's a lot of different parameters that you can feed into it that I could get into a little bit more at courthouse because I know it's going to be too long. But yeah, you can certainly feed it. Let's see. Has everybody seen this for a second? I'm going to go to the notebook real quick. Pull up there. You know what? As long as we have the documentation. That's another thing. You can look at all the documentation for these algorithms, of course. So you can see it does both weighted and non-weighted. And so it incorporates the structure of your graph. It doesn't understand, it's very simple, that's what makes it fast. So it doesn't understand like labels, so it doesn't understand if it's a person or an article. It's just looking at the structure of the graph around it. And so there is some stochasticity, it starts with some random vectors, and then it's doing averages over the neighborhoods. So I think there's I think you can set the parameters of the random walk that it's doing. No, that's a given. But you can see, you can tell it how big you want the embeddings to be, and yes, and you can weight the iterations as well. So, but all of that, if you want like the exact algorithm, is you can look that up. Look up the GDS documentation, and they have them all up there. All right, here.
Yeah, do you mind share some of your customer feedback? How really they benefit from this?
Yeah.
Oh, follow up on that question. Sorry. You can go check Stanford because my work on PhD is graph. So Stanford University, the big group, they have a lot of these algorithms.
They have a great course on knowledge graphs that is free on YouTube. That they have put out, I think, during COVID. So it's a couple years old, so like it's not fully updated, but they have some really cool stuff in there. So a lot of Stanford stuff. To answer your question, I find customers find this useful a lot. I think the knowledge graph, the project that I mentioned before, that's the main thing I'm working on now, turning structured text into a graph is going to be very revolutionary for this customer because they're going to be able to ask those pattern questions, enrich that information in ways that they quite literally couldn't do with unstructured information before without doing a lot of manual tagging. It also allows there to be I know we talk a lot about LLMs, but also knowledge graph as a central repository of information that people can query from is huge for a lot of, again, working in federal government, for a lot of the things that I work on. And so I wish I could be a bit more detailed about my customer use cases, but
for example, like the better customer KPI, is that any of that? How much?
Again, a lot of the customers I work with these days, they can't be super, yeah, go ahead, Sadie.
We do have, if you Google Neo4j use cases.
Okay.
There's an actual page where you can pick by use case. It gives you not only documentation on what different customers have done, but it also gives you links to like videos where customers may have talked about what they've done.
Okay, yeah, that's great. I will check. Thank you.
Can I ask on the graph
Yeah.
that you shared, one of the data engineering side of it? So let's say you have to do this to operationalize this, right? So how would you do this? Would you get these transactions on a daily basis, and then at the end of the day, you with these customers also like relationships, or if your data was real time, how do you do that? What's the complexity here?
We have customers that either data into Neo4j real time. I have customers that do have like a SQSQ and some triggers from their S3 bucket. So I love customers in AWS. So they, every time data gets put into the bucket, they have a trigger and it gets like put right into the database. It really depends on your data ecosystem, but there are plenty of customers that put it in real time. Sometimes they do it once a day. Again, of course, it depends on their specific data pipeline and what makes the most sense to them. Because some customers, of course, they only get the information every day. But it is certainly possible to do it in real time. And there's multiple ways to put the data into Neo4j. You can put it through multiple drivers. You can put it from Python, Java. You can put it in as a CSV. You can, if it's in Aura, in our cloud-based software, there's multiple ways to do it. So it really does depend on the specific ecosystem. It can be flexible.
And pull up on the LLM, just to clarify, you're not eliminating hallucinations here, right? You're just having a much higher quality, dense representation of your data that hopefully the LLM can take.
I should be fair that you can never completely control an LLM, or it wouldn't be an LLM. Right? I mean, if there was no generation, then it's literally not an LLM, right? So to that extent, yes, I can never swear to you on my soul that it won't be that there won't be a hallucination, but you're giving it the results. So you're significantly reducing that risk that it's going to hallucinate. All right, back. Corner.
Yeah, sorry, one additional
go ahead.
question. So in this particular use case, as far as I understand, each node has its own additional fee which is embedded, which is like 1 kilobyte.
Yeah, I'm not exactly sure how large these embeddings are.
I'm just wondering how such a system would scale, because like I worked with Neo4j some time ago, a few years ago, and there were some limits about regarding how much file system can prefetch of how much
heap space.
How many pages can your file system prefetch for efficient and fast work of Neo4j? I'm just wondering if you have a million nodes or
a million
10 million nodes.
Yeah, definitely.
Does it still work? Does it still perform as?
We have customers that have up to 2 terabytes of data in the Neo4j instance. And it also depends, so we have our open source, which is not as powerful as our enterprise edition. So I'm not sure which version of Neo4j you might have used, but we do have customers using Neo4j on very large scale data sets.
I personally have done graph data science on some in banking industry where we had hundreds of millions, close to 1 billion nodes. And then my current project, we're projecting to probably have billions. So there are, and beyond the scope of I'm sure people want to hear, there are certainly ways to optimize it, and that involves knowing Neo4j pretty well. So like on my project with billions of nodes, I am pulling every optimization trick out of the book. So there's certainly ways to make it faster, but it's very possible as long as you understand how to do it.
And then we're adding more and more features where we've just added a feature where you can actually run certain queries in parallel. So you're making better use of the CPUs on your servers. So there's lots of things that we're doing to improve being able to work on very large data sets.
I wonder if you've been able to quantify the reduction in risk of hallucinations as compared to just inputting like a static query into the LLMs.
I have not personally done that. Do you have any? The question was that would we quantify the difference between hallucinations and this method and no RAG at all? I don't even know how you would get. I mean, if you gave it no prompt, it wouldn't even have this data. So I don't know if there's really a fair way to compare it. But that's like research paper quality. I have to think about what would be a fair comparison. I asked the LLM to give me a summer dress, and it didn't understand.
for example, reg-based systems, there is a context adherence score, right? So for example, for that kind of systems, what should be the score, right?
Yeah,
So,
right. Yeah, because if we don't give it anything, I guess what you could do, right? I mean, and this one is hard because how do I know if a customer would actually like it more? Like,
yeah, we need to close the loop.
you
with the
need,
customer.
yeah, right. So I know maybe call H&M. So, but yeah, I think in that case, you either have to close it with the customer, or if you had a data set where, again, like I mentioned, if they're looking for a specific document, like it's a more, yes, this is the right answer, no, it's not, then you could run some more quantifiable metrics.
One last question. So, one of the challenges of LLMs is reasoning, right? They're not the best at reasoning. They're able at extracting information, they're able at language generation, but not at reasoning.
Yeah.
So I'm thinking maybe an improvement, let's say you have some metrics that you can quantify the performance here, would be fine-tune or customize your LLM to think in graph mode. So basically, you give this kind of relationship data set, and you give it the right answer, and hopefully it'll pick up the reasoning behind it.
And that's pretty much what we've done manually, right? So I kind of just was telling you, oh, we did this, we did this, we did this, right? But if you had been the person thinking about that, you might think, I want things that are similar to my query. I want to incorporate the history, right? We're bringing all that intellectual information that the LLM doesn't understand at all, right? We can tell it, hey, talk to a customer like you're a sales representative in the summer, and it can do that. But if I tell it, you know, understand all this information about my graph, you're right, the top of it's kind of not going to do that. But I can tell you right now, I have coworkers who are developing ways to have an LLM like generate your initial data model for you. And so there's a lot of research going on in that space of teaching it how to think graphically. That I already actually, I believe there's already some articles out about that. So.
Maybe an LLM that's purely trained on graph.
Right, on graph.
Purely on graph.
That would be cool.
Yeah, so just knows graph magic.
I like that. I like that.
That's a great place to end it, I think. All right, let's continue the conversation across the street. We need to vacate this space in the next 13 minutes, so.